Now we're into the final modeling video that we're going to go through. Here we're going to introduce some different machine learning methods and a few techniques that are necessary when we get more into machine learning. We're going to use the same data sets we used before, creating an X and a Y training data. And notice I have not standardized these variables. We could do that the same as we did in the last video, but we're going to let Caret do that for us. Then again, I'm going to introduce parallel processing here, and I'm going to get brave and use more of my cores. Some of these you won't actually need that. So if you don't have a lot of cores to run in parallel, I've tried to simplify as much as possible to make it not necessary to run a lot. So here we've got this control function again, or these options. Same method, we can use different methods. This is, I think, most common. Then the number of folds that it's going to use, remember the default is 10, so I'm putting it way down. It's just going to use 2, it's going to split the data in half and use that to look at one side and then the other. And then repeats, it's going to do it only once. And so I think more standard, I think the default is 10 for the number of folds and 5 for the number of repeats, so 10 and 5 would be standard. That will take longer to run, and it isn't really necessary to get up to really large numbers here, but you know, that does, a little bit larger than this would help make the fine-tuning a little more robust, at least we would hope so. A couple of other things. So here in the train function, we're going to introduce this pre-processing. So we could have done this before. What this does is do the same thing, standardize the variables on all of the training data. Of course, one thing we lose is that we're not doing this by year, but it'll at least train, when we look at the training data, it's going to standardize it for us. So if we want to take one fewer steps, we can use this. And it may make some difference on how we standardize, but this is sort of a simple function. Another thing we're going to introduce is this expand grid. And what the expand grid, this can, for each model, there are different parameters that can be trained on, and you can give it a bunch of inputs to use for different training parameters, and you can tell it to look through a certain set of things. For a lot of these, we don't need the expand grid. We didn't use it before, but this forces it to look through a certain number. So remember before we had 9 as the K that was optimal? Well, maybe we can force it to go through only 8 to 10. Like we don't need to do 1, 2, 3, 4, 5 because we know they don't work so well. So we could force it to go through all of these, and we're going to do some different grids that can expand on different models that we're going to use. So this is the same as last time. We're just reducing the number of folds that it's going to use, and we're pre-processing within this Caret function, and then we're only looking over Ks of 8, 9, and 10. Another thing I'm going to do is this systime. So systime, what it does is look at the date and time on your system. So if you're letting this run and you're coming back to check later, if you ask it for that before and after you run the model, then you can see how long it took to run it. So we're going to go ahead and set this up again, force random to be the same for all of us, and we're going to run this. So that time for me, it took about a minute, so it takes a little bit of time. So there are other models. If you're interested, you can go ahead and look up this paper. It talks about why do we need all of these models and are they necessary, and it goes through and tries to find some that are the best of others. But we're going to introduce a few of them here that in competitions and in other machine learning approaches have been fairly successful. So there's some other models we could use. Here our part is a single tree model. There are some others like RF, which is random forest. That is a combination of trees. And the one we're going to work on here is XGBoost, which is a type of forest learning of trees. So it's going to combine a whole bunch of decision trees or regression trees, and it does it in a specific way. And there are different parameters here that we can choose. So we're using the same estimation controlling function, and the parameters that we can tune in this there are more of them. So here in K&N regression, we just had K. Here we have a bunch of them, and each of these talk about how to go through estimating when you walk through the tree-based method. So you can change any of these. We will try to change some of those in just a little bit. These are the defaults, or at least these here are the defaults. Number of rounds is not the default, but there are different defaults, different things you could put in there. Here, the 25 is how many times it's going to go through the data. So maybe more typical here would be something like 100 or 200. Then these here are ones we can mess around with, and we will try to. I don't expect you to understand all of the things that are in this. I just want you to get exposed to them and to understand that there are different things, that parameters that could be adjusted. But this one, there are several that try and make the models not fit too closely the training data. And the reason for that is moving from training data to a different testing data set, often the performance is worse. So one of the ideas is that if we restrict it from fitting the data too closely, then it'll predict better. So here, closer to 0 means ignore more information from the training data. Closer to 1 is fit the data as closely as possible. And so we could mess around with this and try different levels. The depth is how long we want the branches of the trees to go down. So the maximum splits that it will have here are 5, but you could go much further. So smaller numbers prevents overfitting a little bit more. Gamma, this is also one that maybe we can just leave as 0, but if you increase it, and these are whole numbers, so like, or regular numbers, so 1, 5, 10, things like that, that will shrink the estimations. Again, not rely on the training data quite as much. If we want to reduce how much time it takes and how much data it uses, so here we can use the percent, like 100% of the columns. This is from 0 to 1. Or we could use like only 10% of the columns. This is really useful when you have lots of columns. We only have 4, so this isn't incredibly useful here. The minimum child weight is how many at the bottom part of the tree, so like the leaf, the node at the end, how many observations have to be in here. So a larger number makes it fit the data less and prevents overfitting, and it will run faster. But we could have the node go all the way down to 1. So this is from 1 to however many observations are in the data set, but 1 to 100, let's say, for example. And then subsample, this is for each tree, how much of the data we're going to sample back. This is 0 to 100% again, so we're just leaving. These ones we're using all of the columns, and we're using all of the rows of the data. This one is we're requiring at least 10 in each node. So we're going to use all of these. If I were going to train this the first time and I didn't care about how long it took, I would increase the number of rounds, and then I would mess around with some of these. So we'll run this. This is going to be one of our benchmarks. So again, we had the K&N regression before. Now we have this XGBoost, or XGB tree is what it's called. But if we want to read more about what XGBoost is, you can go here. This has a pretty decent explanation of it. We'll run it and then look at some of the output from it. Okay, so this doesn't take very long to run. Some other models like the random forest take a while, or the K&N sometimes will take a long time. And if we change some of these parameters, it can take longer as well. And remember, we are using this control train control up here, where we're only going using twofold cross-validation and repeating that once. So maybe a typical number might be 10 cross-fold and 5, so that would increase how long it takes to run. We can look at what the model output, so it's going to tell us what is the best one, what it ended up using. It says, well, the tuning parameter was stayed at 25. That means we didn't use different values for that. This was the minimum child weight was 10, and right, so just telling you sort of what you did to input into this. And it said it was pre-processed using this cross-validation, and in the end it said it came up with this r squared of 9% and this root mean squared error. So in other words, we didn't run through different options for this, so it just came up with the best it could. Well, if we give different options for these parameters, it'll train until it goes through and finds the best parameter. So we'll do that after this. We can't really understand what this model has figured out. In a single tree, we can look at what that decision tree looks like. But in this case, we just trust that it was working. And one of the things we can do, though, is look and see which variable in the data, in the training data, was most important in the tree. So it comes up with, goes through a bunch of calculations. But in all of those trees combined, which variable matters the most? So this will tell us something about it. Here it shows the log of total assets is the largest, the most important variable here. And then less is leverage, then profit margin, then cash doesn't matter at all. So it's really the log of total assets is the most important variable in terms of doing all of these splits. All right, so that's if we want to know what matters, but it still doesn't tell us much about the model. We're going to have to use the prediction to see how well the model works. Another one that is popular is neural network models. And so there are lots of things we can do to learn about those. Here is one that is not too difficult, gives an easy introduction to neural network models. The one we're going to use is ensemble averaging, meaning combine a lot of neural networks together. That's sort of similar to these random forest or XGB tree ones where it's combining trees together. This one, it's combining neural networks together. And same sort of setup here, we're using average neural net, same control setup, pre-processing. The parameters that are required for this average neural net are these ones. Each model you use have different parameters that are input into it. We can, again, use defaults, but here what we want to do is set these. So let's say we're going to set the decay. So decay is, again, from 0 to 1, and that's how much we back off of the training data. So it basically tell it not to overtrain to the training data. So we can move this from 0 to 1. I just chose randomly a 0.1. Then size is how many hidden layers or units there are in the neural network model. So you can read about how these work here. Really, it just means that larger numbers are more complex. We're thinking of whole numbers. So 1 to, I don't know, maybe 10 maximum. We couldn't keep going forever here. There's a limit to how many we can do. But let's say 1 to 5, or we're going to try two different ones, 1 and 5. So it's going to decide which of these is best. And then bagging is the approach of putting it together. So we're just going to say true. There's this true means it's this bootstrap aggregation. Not necessary that you know how that works. But so the main thing we're doing is looking to see, using different number of hidden units, what works best. And if we really wanted to train the model to be the best model possible, we might include lots of different layers here, or 1 to 10, try them all or something. We could also try different levels of this decay function. These are just parameters we could test. So we're going to run this and again see what the output is. This also, because I've set it up to be as simple as possible, most of these will run somewhat quickly. Of course, anything we change, that there are more parameters to run through, or we're going to go through more repeats on the controlling, it'll take longer. So as soon as that finishes running, then we will look at the output of that model. So again, that was fairly fast. We run this to get an idea of the output of that neural net model. Notice it tried 2 different sizes, and it said that the final model, so the final values used for the model were size equals 5, and then we left this decay as the only option. So we could try more parameters too, and maybe we would get better. Notice what happens is going from 1 to 5, we went from an R-squared of 6% to 9%, or down on the root mean squared error. So or down on the mean absolute error. So the using more number of hidden units improves the model. So on all of these, we might go through and change and keep working these parameters until we come up with what we really think is going to be the best model. You're welcome to fool around with that. You just have to be careful because as soon as you try too much, then it'll run for a really long time. So like we could put in all possible sizes here, all possible decay values, and we could increase this control, how we train the model, and it could run just an enormous amount of time. Okay, we could also plot this just so you know too. So this just plots what we put in this, different values of these parameters. So we've only got 2 variation in the parameters, so it goes from 1 hidden unit to 5 hidden units, and the error goes down. So this is going to be similar to what we did before. We're going to create a prediction with each of these models that we created on the training data set. Again, the KNN regression will take the longest because it has to go through each individual observation. Then what we're going to do is test, once we have those predictions, test the R-squared for each, or something like the R-squared for each of these predictions that we created from these models, and the actual interest rate on the data set. All right, so we ran these predictions. We're going to test the R-squareds, and we can see there is some variation across them. So the KNN regression 66%, the XGBoost 64%, and the average neural net 62%. So we could sort of fool around with these, right? We didn't try and check every possible method, so we could mess around with those and see if on the training data we got something that fit better. So we're going to try a couple of those changes here just so we can see what happens. So here on the training control, we're going to change the number of cross folds or folds of the data to 10 and the repeats to 3. So that will take a little bit of extra time because it has to run through the data a little bit more. But it's splitting up the data more, so it's sort of a trade-off there. So notice everything else here is going to be the same. I'm only going to keep the max depth of 5. Of course, we could mess around with that as well. So the main thing I'm changing here is the cross-validation. Okay, so we ran that one, and notice I saved it as XGB tree 2. So I have the original one. This one is changed by increasing the cross-validation. Now I'm going to do XGB3 and just going to change a couple things here as well. So now this time I'm going to change the number of rounds to 100. I'm going to change the shrinkage parameter, so from 0.01, 0.1, 0.3, it was 0.3 before. And I'm going to change the max depth to 5, 8, and 10. So I could increase these even more and try more options, but I just wanted to give it a shot and try a few more things. Notice because I'm changing 3 here, 3 here, and 100 here, that increases significantly the number of, how much it's requiring to go through the data. So I'm going to run this, and then after we do both of those, we'll look and see sort of how it fits the data. So that takes a little while, but what we can now do is do the prediction for each of these, or the fitted values for each of these two adjustments to the XGB model. And then we can remember the fitness for the first XGB model was 64%. We look and we see we got exactly the same on the second one, so that going through the data using the cross-validation didn't adjust anything. And we get 64.337% when we make these other adjustments. So let's look and see what happened with this model, the one that is slightly better. So we see that it ended with the number of rounds that it went through all of these ETAs and the max depth and chose the one that is best out of all of these. So we can look down here and see, the final values were number of rounds 100, max depth equals 5, ETA equals 0.1. So we ended up at the low end of the max depth and in the middle of the ETAs. So a little bit, we could still sort of adjust other things to see if we get even better, but we're kind of working our way through it. Okay, so now we're going to go to the testing data set, create these same X values. Sorry, in the last one I used the standardized. Here we're not doing that. Then we're going to predict with each of these now I'm calling them predictions because they are predictions on the testing data set. And remember the KNN regression will take a little bit longer than the others. We'll create all these predictions, and then we'll see how it works on the testing data. So once we have those predictions, we can go ahead and test all of these. So remember, we've got the first one is the KNN, second one is the first XGB tree, the third one is the average neural net, and then the two new XGB trees. So the first one, KNN regression, 2.5%. So again, remember, compared to what was happening in sample, so we got these in the 60s. Out of sample, it's much worse, but at least it's, we can see some variation across these. So the KNN regression, 2.5%. The first XG boost one, now out of sample, is slightly better, even though in sample the KNN regression was slightly better. Out of sample, the XG boost is 0.5% or 1.1% better. The average neural net is slightly worse, but about the same as both of these. Then the second one of the XG boost, no difference, so it didn't help at all. The third one, where we included more parameters and varied the parameters more, is actually 268, 265. So it's actually worse after doing that. And so probably what happened then is we overfit the training data, and then it wouldn't work as well in the testing data. So hopefully you can see there are a lot of pieces going on here. It's not that difficult, but one of the challenges that comes up is that we work around with the training data, and it doesn't necessarily translate into better testing data performance. And we have the problem that testing data, that the models just aren't that good when we go to the testing data. So ideally, we would like to improve the models overall and on how they predict out of sample. How do we do that? Well, that's getting better models, and one of the ways we can get better models is, right now we just have these 4 X variables, so these are the only things we have available to us to predict using this data. Well, we would keep working to get better data that would hopefully help us predict even better. So that's part of the art and working through these things. And I think practicing and trying to understand it a little bit and creating your own models is worth trying.